Hello, everybody. Yeah, I'm going to be giving you a tutorial about Google Earth Engine. Now, before we begin, there's a few important things for you to do. First, if you haven't signed up for Google Earth Engine, you should go and do that right now. The links I posted the links in the general Slack channel, or you can just copy the URL there. Go to that website. Here, I'll do it now, and scroll down to the bottom and click the Sign Up Now thing. If you click on it and it takes you to, or it'll ask you to sign in with your Google account. If you don't have a Google account, you're going to need to quickly make one. You sign up, and then in about 5 minutes or so, they'll send you an email saying, congratulations, you've made it into Google Earth Engine. So yeah, I'm going to give you a few moments just to do that right now. Yeah, if you have, while we're doing that, I'll introduce my helpers. I've got 4 members of my group around why don't you stand up, raise your hands, wave. They're going to help you out with the tutorial. If you get stuck, if you run into some errors, some issues along the way, raise your hand or wave to your nearest person, and they will come over and help you out. If you just have kind of a general question, you can just raise your hand and look at me, and I'll know that you just have a question. You don't need help from them. Some other thing to do is open up the tutorial website for this tutorial. It's the second link. I also posted in the Slack, or you can, again, copy the URL there. It should look like this. It has all of the tutorials that we're going to be covering today, plus a few bonus ones that we're probably not going to have time to do today. But you can look through them out there at your own leisure. OK. Was there any issues with people signing up for Google Earth Engine? Has anybody not done that or still struggling with that? OK. We're going to go on then. OK, so an overview of how this is going to work. I'm going to give you a quick introduction to sort of what Google Earth Engine is, how it works. Then I'm going to introduce you to the JavaScript API, which is what we're going to be using the whole time for using Google Earth Engine. And then we're going to have a series of 4 tutorials where I'm going to give a little introduction to how they work, and then we're going to go into the code and actually code up these tutorials to show off some of the functionality of Google Earth Engine and give you sort of a base of tools to play with on your own. And then we're going to wrap up with some helpful hints and some further resources you can go to. OK, so what is Google Earth Engine? Well, it's a few different things all bundled into one package. It's a cloud-based geospatial analysis platform from Google. So what that means is it's just a way for you to connect to Google's cloud computing platform and use their resources for your own geospatial computational needs. It's also a catalog of geospatial data. So it's got 5 petabytes of geospatial data. So that's like satellite imagery, terrain data, land cover, also things like population, or I believe there's a malaria risk data set in there. So there's a wide variety of all these kinds of spatial data sets that you can harness that are available there. And it's also a library of geospatial analysis tools. So it's also got the base kind of tools you would expect from a typical GIS system like ArcMap, for example, for processing these data sets. So how does it work? Well, the basic principle is you write some request. We're going to be using the JavaScript to write our requests. You write your requests. They get sent to Google's servers, where they have all of the data sets, all of the algorithms, and all of this computational power. They run through your requests, and then they send you back whatever results you asked for. So that last part is key. It only sends you back what you asked for. And Google Earth Engine is a little bit lazy. So if you don't ask for anything, it's not going to run anything. It only runs things that are necessary for you to get back whatever result you asked for. So that's something to kind of keep in mind as you're going through this. OK, so why should you use Google Earth Engine? Well, one, it's free cloud computing. It's free for educational and research purposes. There's a license for commercial use, but I'm unfamiliar with how that works out. You have access to petabytes of data from any computer. You're not limited by what your computational hardware is. Like the laptop I'm working on it's not a bad laptop, but it certainly couldn't handle any of the geospatial tasks that we're going to be doing in our tutorials today. And you also get fast global scale analysis. So you can look at problems that are much, much larger than you could ever do on kind of your local hardware. And you get them really quickly. It's not like something you set up and let run for a day and you get your results tomorrow. You push the button and you get your results in a few seconds, which helps a lot with sort of fine-tuning your processes. Also, many of the roadblocks in working with doing these kinds of large-scale computations are just taken care of by Google. You don't have to be an expert an expert data scientist to be able to do some of these computations. Things like parallelization or other computational tricks to speed up your computations. You don't have to worry about that. It's all taken care of by Google's cloud servers. And finally, sharing your results is very easy. As you'll see, we'll do some examples. It's as easy as copying a link and sending it to somebody. So it's very easy to do that. Some things that are relevant to water, some data sets that are relevant to water. There's sort of a spectrum of data sets available in Google Earth Engine that range from sort of your raw data, your raw observations, all the way to things that I call end-user data sets. They're these kind of data sets that synthesized all of this raw data and tell kind of a cohesive story about some geospatial phenomenon that is sort of ready to be interpreted. But it also has these data sets that you can then use as a launch point for your own analysis. And sort of in the middle are these models that grab data from a bunch of different sources and put them together and then put the output up on Google Earth Engine as well. So that's like climate models and weather models. So one example of this end-user data set that I want to highlight is this Global Surface Water Explorer. Where did I put it? There we go. So it's this tool that was developed that shows the water, how water has changed since 1984 around the globe. And you can go to this link. The link is in the Google Earth Engine page in the introduction to Earth Engine part, if you want to go explore this. So this is just like an explorer that they made for it, but this data is also available in Google Earth Engine so that you can play around with it and use it for your own analysis. And there's lots of cool things. I'll just show one kind of example. I do a lot of work in Southeast Asia on reservoirs, and something that I find kind of cool is that you can see that this spot, the water, green is an increase in water, so you can see that in these places. Oh, you can't see my screen, can you, over there? Sorry about that. Hold on. There we go. What is this? Nope. Loading. Oh, okay. Let's see. I'm just going to refresh this page. Oops. Well, okay, so it seems that it's something is up and I can't quite connect to it. But we can come back to that example later. Okay, so let's talk about what Google Earth Engine is not designed for. There we go. So it's not designed for cartography. You're not going to make professional scale maps in here. It lacks a lot of the tools to make a really nice looking map. It's really good at visualizing your data, but in terms of then making like a really professional looking map out of that, it doesn't really have all the features there. You're going to have to export your data to some external tool for making that. It's also really bad at heavy-duty vector operations. That's things like looking at polygons or sets of polygons or sets of points data. It's fine at working with a reasonable amount, but if you then wanted to say, I don't know, if you had for some reason had the boundaries of every property line in the entire US and you uploaded it, you want to do something with that, it might not be too happy with that. It's really more designed to handle gridded data, these gridded kind of data sets. It does not let you do any kind of do-it-yourself computational options. So if you are a data scientist and you have all these ideas of how you want your data processed, then maybe Google Earth Engine is quite not the tool for you. The price you pay for having it take care of all of these parallelization and computational things is you don't get to control any of the options that go into those. That hasn't really impacted me in my work because I'm not a data scientist and I don't really care how it gets done. I just need it to get done. Okay. So how do we connect to Google Earth Engine? Well, there's two APIs that you can use. There's the JavaScript API, which is a web-based graphical user interface. It lets you do some rapid visualization of your outputs. It enables you to store, share, and keep version history of all of your scripts that you write on there. You can also do a customizable user interface, which we'll have some examples of that later on. And it's also this is the easier API to learn because of all these things, because of the rapid visualization of your results, and because of how it lets you share and store scripts. The Python API is you connect to the Google Earth Engine server from your local Python installation. The visualization in that case is left up to the end user. So you also have to know how to visualize your data using Python tools. The benefits of the Python API is you can connect in your Google Earth operations into any kind of local workflow. So if you have a model that you're running and you want to incorporate some Google Earth Engine, some data that you get from Google Earth Engine into there, Python, the API is what you'd want to do. It also, in my experience, it is more difficult to debug just because there's kind of this extra step of connecting the server from your Python installation, whereas the JavaScript API is sort of already connected and there's no issues there. So that's why we're going to be using the JavaScript API for this. Okay, so let's jump in and see let's take a look at the JavaScript API. So everybody who signed up for Google Earth Engine just now, can you check your emails and make sure they check to see if you've got like the email from Google that says that you're signed up? Some people are shaking their heads that it hasn't worked. Can you try going to, I guess, here, we'll do this. Everybody try going to this website, the code.earthengine.google.com. And then I guess raise your hand if it doesn't take you to a screen that looks like this. Okay, so everybody is looking at a screen that looks like this. Awesome. All right, so this is the JavaScript API. This is the website that you go to. You might want to bookmark this website. This is where you'll go to every time you want to use the JavaScript API for Google Earth Engine. So let's just explain kind of a little bit of what you're looking at here. Okay, so this main white part in the center, that's your code editor. That's where you're going to be writing all of your requests, all of your scripts for Google Earth Engine. When you write something and then you click run, it will run it. It'll send that whole script to Google Earth Engine. They will run it for you and send you back whatever you asked for in the script. down here is the map. This is where you can visualize things. This is where you can visualize your data. Oftentimes, the stuff that you request back is usually going to be either in the form of a map, so something that you add to the map to visualize your data, or some kind of chart, a chart that you, a time series chart, or just some value that you print. And if you print something, it'll show up here on the console to the right. Over here on the left, this is where all of your scripts are. I have a few repositories here, but if you just started Google Earth Engine for the first time, you should just have the one that's your default repository. That's where all of your scripts will be saved for future use. This docs tab, this is where all of the things, this is a list of all of the things that you can do in Google Earth Engine. This is all of the tools that are available to you. It's at first a list of the different types of objects. It might seem a little overwhelming. We're only going to use a few of these, so don't worry too much. But it's a list of all the different objects. And then if you drop them down, for example, I'm going to go to number and drop it down. It's a list of all of the different operations you can do on that object. I would highly advise you to stick to only things that are in that list. These are the only things that will run on Google Earth Engine servers. If you do some regular JavaScript functions, it will then spit those back to your browser and run those in your browser, and then go back to Google Earth Engine. And that increases your time by a lot. So I would highly suggest to just stick only to the functions that are in here. And this is totally searchable, so you can search for what you want in here. For example, if we wanted to know how to add two numbers together, you can search for add, and you can find number that says add, and that'll tell you how to add two numbers together. Okay, so there's a few other features that we'll look at as we go, but let's get started. Yeah, okay, so first thing that's important, double slash. I should say, is that too small for everybody? Should I zoom in one more? That's fine, everybody can read it from where you're sitting? Awesome, okay. So double slash is how you comment things out. So it's just a comment, it doesn't add anything. So in some example scripts that I'll give you, you'll see a lot of green. Those are comments, they're not running at all. It's just telling you, what's going on there. Okay. So, and then, all right, so let's do print next. So to put something out to the console, to get some output out of whatever you're doing, you say print. And we're going to do our hello world. So go ahead and type that in and then click run. You notice it prints it out to the right there. It prints it out to your console. Anytime you use print, it'll show up in your console. The only things that show up in your console, by the way, are when you print something and when you get an error. When you get an error, it'll be big bright red. You'll know. Okay. So let's see. So to define variables in JavaScript, you need to use, the first time you use them, you need to use var, V-A-R. So it's var, then a space, and then whatever you're naming the variable. So let's just do x. I'm going to say x equals 3. And then we're going to print that. Let's click run. You'll see 3. Cool. Then you can say something like, I don't know, x plus 2. Print x plus 2. And you'll get 5. Cool. But remember, that plus is not a Google Earth Engine algorithm. And that 3 that we made is not a Google Earth Engine object. We need to make, these are running in your browser, which is fine when we're just doing 3 plus 3, or 3 plus 2, but when you then go to do some spatial data sets, it might not be so happy to be running in your browser. You want to run it in the cloud. So we're going to go back to this x, and we're going to define it as a number, as an Earth Engine object. So to do that, it's always EE, and then whatever the object is called. So EE number is how you make an Earth Engine number. Now, for numbers, it isn't so important that you turn them into these Earth Engine objects. This is just kind of an example for how the syntax is going to be later on. Okay, so now that we've turned it into a number, instead of plus, it's dot add if we want to add 2 to it. So, and you can find that, again, if you go look in your docs, you go to number. That'd be easier if I didn't even filter. OK, get rid of that. And go down to number. You can see all of the different functions that there are. And we did the .add function. You can click it on and see some information about what it is. So we're just adding 2 to x. So if you do that and click run for the first time, you see that if you notice over on the console, there's a little wheel that spun for a little bit. That's because now we're sending it to the server and getting the result back. So for just this simple calculation, it's actually slower to send it to the server because we have to wait for it to, there's the transit time. But for much larger things, it's obviously going to be faster. OK, are there any just kind of questions about just kind of this very basics about how the JavaScript syntax and how the Google Earth Engine syntax works here? Awesome. OK. Oh, a quick note about the syntax, and this is, I'm terrible at this. At the end of every line, there is supposed to be a semicolon. I always forget the semicolon. The code will still run without the semicolon. It's just sort of more of a formality to show you where the end of that line is and where the next line is. I'm always going to forget the semicolon. It's just a bad habit that I have. So I apologize for then passing this bad habit on to you. But if you look at some code, you'll see a bunch of semicolons at the end of the line. That's just all they are. They're just saying this is the end of the line. Google Earth Engine knows when the line ends. Doesn't really need the semicolon. But OK, so now we have this script. And you see, since we've typed some stuff in there, you can see we can go and save. So let's go ahead and just try this and make sure this is working for everybody. If you go and click Save, you'll get to choose what the name is. I have a few repositories here. You'll only have the default one if you just started. So don't worry about that. But then you can change, I'm just going to call this the Hello World file and say OK. And then if you go over to your scripts, you'll see it should show up in your repository, and you'll have it right there. And you can manage things. And there's also this little revision history button you can click on. If you had saved this multiple times, you'd be able to look at the different spots that you saved it and roll back to old versions. So if you accidentally tried some changes and broke your code, you can roll back to these old versions and fix them up. OK, another feature, get link. If you go and click this get link button at the top, you'll notice that your URL all of a sudden just added a whole bunch of stuff at the end. That stuff, if you then copy and paste all that stuff and put it into a new tab, it will open up a new Google Earth Engine thing, and you can click Show Code, and it'll be the exact same code that you have. So this is one way you can really easily share your code, is you just click Get Link, send it to somebody, it'll give them a static version of the code. Now, it gives them a snapshot of the code as it was when you saved Get Link. This is not like a version syncing kind of thing. They won't be able to work on, like, if I then made changes to this code, I would have to save it as something else on my own file to have access to it. There is a way you can open shared repositories and share between those so that you can collaborate with people on the same code. We're not going to go into that in here, but that's also something that's possible when you make a new repository and go to, there's some configure options there, but we're not going to get into that right now. So that is, any questions on the kind of saving and sharing thing? OK, awesome. All right, so now we are going to go and load up some satellite data. So let's look. We are going to load in the Landsat 8 collection. Landsat 8 is a satellite imagery mission to take pictures of the Earth, essentially. So we're going to do that. We're going to define a variable. I'm going to call it Landsat 8 collection. OK, and now we're loading in an image collection. This is just you can think of this as a time series stack of images, and an image is just kind of a gridded data set. This will make a little more sense when we get into it. So if that doesn't make too much sense, hold on for a minute. We'll get there. So to do that, it's ee.image collection. And make sure that if it turns dark purple, that means it's you're creating some kind of Google Earth Engine object. Make sure to capitalize the C and the I in image. OK. So now we need to find out what the name of the collection that we're after. So actually go up ahead, go to the search bar, and we're going to search for, we're after Landsat 8. You type that in, and you'll get a whole bunch of options. We're after the top of atmosphere, the TOA, Tier 1 reflectance. Don't worry so much about what that means. It's just right, a reflectance at the top of the atmosphere, but it's a measure of how bright the Earth is how bright the sunlight from the Earth is at different wavelengths. So let's go ahead and click on that, and it opens up the documentation for that data set. Now this is how you'd search for any data set. You wouldn't have to search for the name of the data set. You could search for imagery or precipitation or something, and it would bring up a list of all the data sets that have that tag. So we open it up, and we see it gives us a list of what the bands are. Now for bands, if you're unfamiliar with how the kind of satellite data terminology, it's you can think of these bands as each one of these is a gridded data set, and they are and each one is a measure of how bright it is at that wavelength. So how much blue is there, how much green light is there, how much red light is there, how much near infrared. So we've got all these different bands. So you can think of this one image as kind of is already a stack of these different types of data. But what we're interested here is we're after this collection ID. So go over there and grab that collection ID and copy that, because this is the name of the thing that we're going to call. So go put it in quotations. Oops. Make sure it's on one line. Put it in there. And now we have loaded it, and let's go ahead and print it. So go ahead and print your Landsat 8 collection, and go ahead and hit run. Uh-oh, what did we do? Well, we just tried to load the entire Landsat 8 archive in our browser, which is terabytes and terabytes of data. And even Google Earth Engine has its limits. It's got these caps. It'll cut you off if you try to do something ridiculous like that. So let's go back to that print and modify it a little bit, just so we can see what we're dealing with. So put a dot limit, and I'm going to limit it to 5. Put a dot limit after that and click run. OK. OK, now we've got something sensible. We have an image collection with 5 elements. So what that limit did is it just said, only give me 5 elements out of the Landsat archive. I believe it picks the first 5. So it's just the first 5 Landsat images ever taken. It's showing us right there. So let's go explore this a little bit in the console. So you can drop it down. You see it says features, and it's a list of 5 elements. There's 5 different images in our thing. And let's go ahead and drop that features list down, and you'll see it's 5 images. So let's go ahead and expand that a little further. Let's look at what's inside each of these images. So if you drop that down, you see it's got bands. If we look in there, it's just telling us what all the bands are, and these correspond to those bands that were in the documentation. And then let's look into properties. You see we got a whole bunch of properties. So some important ones to look at is this things like cloud cover. That tells you how cloudy the image is. We're going to use that a little later. There's other things that might not make much sense or are of any purpose for what you're doing, but there might be some stuff in here that is of use to you. So I'm just pulling this up to just show you that there's all this information that's in there, and we can use this information to pull out the exact images that we're after, and that's what we're going to do right now. So I'm going to close that up. OK, so we need a way of filtering down this collection, because it's still huge. We only printed 5 of it, but it's still all of the Landsat archive. Let's see. So we're going to filter over a location first. We want all of the images over a specific location. So we're going to use Lake Powell as our location. And this being Google, the search bar does everything. So you can search for Lake Powell, and we're going to do the one in Arizona. Feel free to do the one in Australia if you want to, but I'm going to do here. So let's look at the map. So if you hit enter, it'll just take you to Lake Powell. And we're going to make a little point. So we're going to use these tools over here, the geometry tools up in the top, the left of the map. What these do is these are a quick way to make geometry on your map. So we're going to click on this point. I'm going to click the point, and then I'm just going to put it right here, right on the name Lake Powell. You can put it anywhere around here. You can actually put this anywhere you want, and I'll give you some time a little later to play around with this. So I'm just going to click once, and then make sure you click exit, or it's going to put, if you keep clicking, it's going to put more points around. We're just going to click exit. All right, so let's go back to our code editor. If you look at the top, you see now we have this imports. Every time you add kind of a geometry there, it'll show up in the imports. These are things that you just have. It's kind of like the variable was generated. If you want to see the exact code that makes it, there's this little blue box. And if you click it, it'll show you the exact code that is essentially running before your script to make this thing. So right now it's just called generically geometry. We want to give it a little more descriptive name. I'm going to call it Lake Powell. 2 L's. 2 L's in Powell. OK, so now we have this. We have a point that's called Lake Powell. So let's go back. Let's try and extract a single image from this image collection. In fact, let's try and find the least cloudy image. We just want a cloud-free image of this location. Right now, we don't care about exactly where it came, when it came from. We just want a cloud-free image. So let's try and do that. So first, we're going to define a new variable. We're just going to call it image. Let's see. Image, ee.image is what we're doing. So let's see. I'm going to put in, there's double brackets here, and that I'll explain that in the end. But what we're going to say here is we're going to put our collection here. And set 8 collection. Then we're going to send one of the brackets down. We're just going to move that down a little ways. So we are going to first filter this by the bounds. So to do that, you do dot filter bounds, and then our geometry that we made, Lake Powell. A note about the syntax, I could put this like that, and it would be the same. We're just going to be doing a few of these filters, so it's easier to read if you put them down. And I just tab in, so it's just kind of a best practice. So dot filter bounds, Lake Powell. So let's go below where you close that bracket, and let's print this image. Oh, I don't think this is going to work yet. Never mind. Scrap that part. OK, so what this is doing is it's getting rid of all of the images that don't intersect with our spot. So we're only left with the images in the collection that intersect the point that we made. So now we've dramatically cut down the number of images because we cut out the entire world except for Lake Powell. OK, so now we want to get, now let's say we're only interested in images that were taken in 2018. So let's go on another line. Let's do filter date. We're going to filter from 2018, 0101, and we're going to filter to 2018, 1231. Make sure that your comma ended up between the two. Make sure your comma isn't orange. Make sure it didn't end up inside one of those parentheses or apostrophes. OK. So now we've gotten rid of all the images that were we've limited down to only images that were taken in that time frame. OK. And now we want to say, well, we only care about the optical bands. We only care about the visible and the near infrared bands. We don't care about the extra stuff that was tacked on, any of those quality control bands or anything like that. So we're going to do a dot select, and we're going to give it a list of, let's see, oops, dot select, and then we're putting this in apostrophes, B1-7. So what this does is it looks, if we go back to our printed image collection, we look at the bands that are in there, it's going to select bands 1 through 7 and get rid of all this extra stuff that we don't want. Okay. And now we are going to, now remember we want a cloud-free image. So let's go ahead and sort this by our cloud cover. So we're going to do dot sort cloud cover. And then finally, we want the first one. So what that'll do is dot sort puts them in order of that cloud cover property that I showed you. And then dot first just pulls the top one off that list. So it's guaranteed to have be the lowest cloud cover image in 2018. All right, so now up until that dot first, we still had an image collection. It wasn't an image yet. We still had a stack of images. That dot first pulls the top one off. We're at an image. I think we've succeeded. So now let's print this out first and just see what we have and make sure that we only have one image and make sure that it is cloud-free. So print image. And with print, you can always do comma and then give it kind of a tag to tell you what it is you're printing. So I'm going to do like that. Go ahead and run that code again. And you should have this kind of thing over here, Lake Powell L8 image printed. Okay. Is everybody okay with that? Everybody's there? Yeah. No, so what we did is we sorted all of the images in that year by cloud cover. So descending, so lowest cloud cover on top, highest cloud cover, and then we just took the first one off the top. That's how we got down to one image, yeah. That's a good point. So a common theme of how this is going to work, of how a lot of my workflows in Google Earth Engine are, is you start with an enormous amount of data, and the goal is to then reduce it in a meaningful way into something that's useful. That's kind of the whole point of what we're doing here, because right, it's easy to say that 5 terabytes of Landsat data that's not really meaningful if you look at it. So our goal is to then reduce this data down into something that's meaningful. So usually that means into a single image that we can then map, or a single time series that we can then plot. So that's kind of the goal behind all of these, and sort of using Google Earth Engine in general is reducing all of your data down into something that's easy and manageable that you can then take out of Google Earth Engine and use. Yeah. Okay. Let's see. I'm going to wait until some of the questions have been taken care of. In the meantime, so before we move on, check out this. Take a look around in this Landsat 8, the thing that we printed, and confirm that it makes sense and it is what we want it. So if you print it out, you get bands. You see the bands. You get. You see we only got the 1 through 7. Perfect. Those are just the optical ones we got. And if we take a look at the properties, you'll see that cloud cover is 0. So perfect. We hit an image that has 0 cloud cover. Everybody else got that same kind of thing who got this? Cool. Cool. You got cloud cover as 1.24. Interesting. Is your point in the exact same spot? It might be that you're on the edge, and we'll see when we print it. We'll see when we add it to the map. If it could be that your point is at a different spot so that an overlapping image goes to somewhere else. Right. Yeah, yeah.
Filter bounds is not a function.
Dot. Okay, I see. That second parenthesis, take it off and put it after first. That one at the end of your, yeah, yeah. Yeah. Okay. Yeah, this might be a common hang-up for if anybody is still having issues. Check to make sure that there's only one parenthesis at the end, one closed parenthesis at the end of this line, the line 11, or yeah, this line right here, and make sure that the parenthesis that would be there is actually down here to close it out. That's an important part. Yeah. Okay. Okay, I guess I can also take this time. If you're also stuck, this one is just very loosely following the code editor example. If you go to the website and you look at the code editor example, this one is sort of loosely following it. The next the tutorials after this will all sort of follow these tutorials exactly. So you can also kind of follow along there. And all of the code snippets that we're using are actually just in there. So if there's kind of a long, complex thing that you don't really want to type out, you can go in here and just kind of grab it and copy and paste it into your code. So for example, this long kind of code, this long chunk of code that we just did, you can go and grab that and paste it into your code and run it. There's also a link to the full code at the top of each of these tutorials that you can click on, and it'll open up the code that is all of the code that was in there in a Google Earth Engine thing. Okay, I think we're going to move on here. Oh yeah, sure.
When you're looking at the properties, is it like displaying the information from the metadata file?
Yeah, exactly. The properties are just, it's the metadata file for that. Yeah, and certain products some products have more metadata, some have a lot less. There's also the option, sort of an advanced technique is you can actually add to those properties. You can add things to the properties and then sort by those. So you can, if you have some kind of qualifier, some kind of source. I'm trying to think if any of the tutorials will have that, but I'm not sure. But that is an option. If there's a certain set of metadata that isn't in there, but that you can create, you can put it in there yourself and filter it that way. Okay, so let's finally go ahead and add this to the map. So to do that, the command is map, capital M, map.add layer. Oops. Layer also capital. Oops. You do image. Okay, so the first argument for map.add layer, and if you want to see all the arguments, you can go to the docs and search for map.add layer. And well, let's go down and you find map.add layer. There's a bunch of arguments to put in there. The first one is just what image you want to display. The second one is visual parameters. We're just going to keep that blank for right now, so do the closed squiggly brackets. And then the third one is a name. So we're just going to call this L8 image. So go ahead and run that. Notice that you don't have to save your code to run it, which can be a little bit dangerous because you always want to, you want to make sure that you are saving your code and not losing all of your work. So I'm just going to hit another save just to keep this. All right. So if you go ahead and add that to the map, oops, I'll keep that command up there. You'll notice that it looks kind of ugly. It doesn't look like a satellite image. It's this weird kind of dark. It's not taken at night. And the reason for that is because Google Earth Engine doesn't really know how to display this data in the way that we want it to yet. So we need to tell it. So one way to kind of adjust what you're doing is after you've added something to the map, this little layer manager will show up. And you'll see our image right here. That's why we named it, is so that we could see what the name was in the layer manager. if you click on the little gear, it'll open up the visualization parameters. So in order to get to get like a true color composite, what you would see, with your eyes, for Landsat 8, it's bands 4, 3, and 2. That's the red, green, and blue. That's the visible light bands. So go ahead and change those to 4, 3, and 2. And then the range, let's set the maximum on that to 0.5. Now I know you don't. I know that that's a good range. You can play around with the range for the type of data that you have. For right now, just kind of accept that that's a good range to put it at. So then go ahead and hit apply. And you should have something that looks more like a desert and a lake. Hopefully. All right. Did everybody get kind of an image that looks like that? No, you're shaking your head. What happened? What does it look like? Slightly less gray. Okay. Make sure that make sure that your bands are 4, 3, and 2. That's kind of the important part. Feel free to also experiment with the bands. Try to play around with, I'll give you some time to play here in just a minute with this. But yeah, feel free to play around with the bands and see, what kind of changes. Keep in mind that it's different kinds of light that you're showing with this. Right now we're just showing the visible light, so we get something that looks like it looks like. Okay. Now, if you go ahead and click Run again, here's the downside of using a layer manager. Go ahead and click Run again. It goes back to the original. You lose all of those parameters. So we have to actually put those parameters in our when we add it to the map. So go ahead and go up to the map and hit. So we need to tell it which bands to do. So we're going to say bands, and we need to give it a list of our lands. So B4, B3, B2. Okay. Be careful with typing this out. Make sure that each band name is in its own set of apostrophes, and make sure that that the commas are outside of those apostrophes. That's a pretty common mistake that I make. So we got the bands, we got the right bands, and now we just need to set the right maximum. So we're just going to say 0.5. The spaces don't matter. I add the spaces just to make it a little cleaner. That's just my own kind of practice. So if you do that and hit run, it should look exactly like how it was when you played around with it in the layer manager. Yeah. Where did you pull the keywords for that? The keywords? Oh, the bands and max. Yeah, it's a little bit hidden in the documentation. So let me show you kind of the rabbit hole. This is one thing that's a little bit trickier to find in the documentation, but I'll show you kind of how we found it. So in the docs over here on the left, the map.addLayer, we found the map.addLayer thing. If you open that up, it tells you what the arguments are. And if you look at the second argument, it's viz params, the visualization parameters. For images in image collections, see data ee.data.getMapID. So then if you go and search for that in the docs, it has a list of all the different things you can set. So it's a little bit of a rabbit hole to find those. Yeah, there's not that many, so it's not, once you know them, it's kind of like you just know them. But yeah, that part is a little bit annoying. Okay, so now we have this image. All right, one last thing I want to show you, and then I'm going to give you 5 minutes to go and play with some things with this. Go over up to the top where the console is and click on the inspector. So if you switch to the inspector tab, up at the top right here, and then you mouse back over, you'll notice your mouse changed this little crosshair. And if you click anywhere, oops, it will show you what the band values, what the value of all of those bands are wherever you clicked. So this can be a useful little tool at quickly kind of identifying certain features of your raster. And we're going to come back to using the band things some more. And apparently there's a chart view. I have not noticed this before. I guess this is a new addition since I learned how to use this. And you can click on the chart and look at kind of how the value of the bands laid out in kind of chart form for wherever you clicked. So you can try clicking on different parts of the image and seeing the different spectral properties of what you're looking at. So, all right, I'm going to give you 5 minutes. Play around with kind of the image parameters, and also try moving your dot to someplace else and get a different image. Try playing around with it. If you have any questions, ask. Yeah, so 5 minutes. We'll come back at 11:15, and yeah. So go play around with the image visualization. Yeah. Cool. Okay. Okay, something I forgot to mention. If you go to make a second point, under this geometry imports thing, you have to click new layer. Otherwise, it'll make the point under the same name as your original point. If you do 2 points and you say filter, you'll get images. You'll get the images from both locations. But when you then go say first, it'll just grab whichever one happened first. Whichever of the cloud-free images was taken first.
And what happens if you have two geometry? You have two points that is separate layer.
Oh, as a separate layer? Then you have to change the name of where you filter. See in like Powell? Like if you would give it another name, you'd say.
Oh, but then one at a time.
Yeah, and then you do them one at a time, yeah. Yeah. Okay, I think we're going to come back. Did anybody play around with the visual, like the bands, like which bands you're visualizing at all? Or did most of you just like go to a different point and try and visualize it there? Yeah. cool. Did it worked out? You got a nice cloud-free image of wherever you're looking? Very cool, very cool. Okay. So some quick things before we go on to the next tutorial about getting help. Where do you get help when you get stuck and you're not here and you don't have people to ask questions for? Well, the first place I would go if you're just trying to figure out how to use your stuff is go to the docs. It's really searchable. That being said, some stuff is okay. Okay. All right. Everybody can hear me now? Okay, cool. Yeah, all right. So first, check out the docs. Try and find what you're doing for, or even search for if you say, like, oh, how do I add two images together? Maybe search for image add, and it'll give you, and it'll pull up the stuff for that. So once you've, if the docs just aren't doing it for you, they don't have enough description, then you can go to the help button. And there's a lot of things to look under here. There's the user guide, which is it's like the docs, but a little more fleshed out. There's a few examples in there. It's very useful. Then there's the help forum. The help forum is where you can then go post and ask for help from other Google Earth Engine users. And the people on there are generally pretty friendly. They're generally very helpful to beginners and that kind of thing. You might have to request access the first time to get in there. Like if you click on it, it might not let you access. You just have to click request access and you'll get in within a day or so. Then there's the, let's see. There's the data catalog if you want a more friendly way to browse the kind of data that's in Google Earth Engine. More friendly than the search bar, I mean. Let's see. And lastly, another great place to go, if you go over to your scripts and you look down in examples, here, if you drop that down, you'll notice that there's a whole bunch of different types of things, different folders, and in each of these folders there's a whole bunch of examples. If you go in there, I'm going to quickly save my script so I don't overwrite it. So if you go in there, like let's just look in image, for example, and you look at, let's just grab the first one. If you click on it, it opens up a really simple script that has a little example. You can run it right there. You can make changes to it and save it as your own thing. So all of these examples are incredibly useful. For the first few years that I was working on Google Earth Engine, everything that I wrote was just a variation on one of these examples. I just took one of the examples and twisted it into what I needed to use. So these are very helpful, and again, the stuff is right there, so you can just click. I don't even know what some of this stuff does, but you click on it and it runs and does whatever it says it does. They've got some decent documentation in there too. So I found these very, very helpful in doing all sorts of different things. So if you have some kind of task and you're like, I wonder how I do that in Google Earth Engine, try taking a look in the examples and seeing if there's something in there that's a little bit similar to what you're trying to do. Okay, so now we are going to move on to, I guess, the first tutorial. So go in here and go to, don't mind the schedule times in here. I figured those would not be right at all. We're going to get, there's a lot of time left at the end that's unaccounted for in here. So don't worry about that at all. And all these tutorials are staying up, so if we don't get to some stuff, you can look through them on your own time and do that sort of thing. So let's go to accessing satellite imagery. Now there's some stuff in some of these tutorials where it is just kind of a chunk of code, a chunk of kind of like codes, some nasty stuff that would be to copy off the board. So it would be easier if you just had this open and you could copy and paste from there. But you don't have to follow along there. You can just follow along with what I'm doing on the screen. Okay, I'm going to quickly switch mics here. Okay, that's good volume. Cool. All right. So in the last example, we just looked at how to just find any image. We just wanted to find any cloud-free image of our spot. In this one, we're going to be saying, well, what if we have a region that's bigger than just one image? If you look at lot of satellite data products are collected and shared, they collect in these tiles, in these tile formations. You can see here, this is for Landsat over the US. You can see that, so Landsat collects every 16 days. So every 16 days, it will, if you're interested in, you say that's one square on there, every 16 days there will be a new image of that square, always over the same spot. So then the question is, what if you have a region that's larger than one of those spots or extends across 2 tiles? How do we gather all this data and put it together into something that makes sense and is cohesive? So what we're going to be doing in this example is we're going to look at a water basin, a river basin, and we are going to examine, we're going to try and find the peak vegetation. What's the peak vegetation in that basin? And you can actually pick any basin you want in the US. I'll show you how to do that. The basin that in the default is a very agricultural basin, so the peak vegetation could represent kind of the peak growing season and might inform on all kinds of water balance things, how much water need they have there. So that's what we're going to be doing. We're going to take a time series of all this data and we're going to synthesize it down and calculate the maximum. What was that? Sorry about that. Okay. Yeah. Let's see. Okay. So first thing we're going to be doing is we're just going to load a vector boundary of all of the watersheds in the US of this size. Let's see. Switch over to this. Okay, I'm going to switch over to this. I'm going to make a new file. I'm just going to say new file. Let's see. Let's just call this, I'm just going to call this example 2. Put it in my Waterhackweek. Okay, another quick way, if you just want a blank file, is just open up the code editor in a new, what is going on? Sorry, turn this off. There we go. Okay. You just open up the code editor in a new tab, and you'll get a blank file that you can then work with. That's usually what I do because it's quicker than making a new file and then going over and selecting it. Okay, so let's go ahead and open up this. Let's load this water boundary data. So this is data that is available if you went and searched for, let's see, what is it called? Let's see. Basin boundary. We're going to use this one right here. So it's a publicly available data set. So let's define it. Water boundary data equals, and this is, instead of an image collection, this is a feature collection. It is a collection of vector data sets, a vector of collection of vector data sets. Okay. And we want this one, this 06 one. So I'm just going to grab that name. You can copy it from here. You can copy it from the tutorial website. I'm going to put that in there. Okay. And now let's print this out. And we learned our limit with printing, or we learned our lesson with trying to print things as soon as we load them in without filtering. So we're just going to limit this to 5, just to see kind of what the structure is like. Go ahead and run that. And if you're still in the inspector, make sure you switch back to the console. Why did it happen twice? There we go. Bug, I guess. Okay. Feature collection. So you should have this feature collection that has 5 elements. If you drop that down, let's look at the individual features and see what they have. So let's look at this feature. It's got geometry. You see, it's a very complex geometry. It's got all these vertices. But we're not interested in that. We're interested in the properties. So it's got a few different properties. So you could say, I want the largest watershed in this data set. You could then say sort by area in acres and take the top and take the bottom one, I guess. You'd have to do, there's an option in sort to reverse it, but you get the largest one. What we're going to do is we're actually going to use the name to find the one that we want. And you're going to find whichever one you want. And how we're going to do that is we're going to add this to the map. So you can take a look at what they look like. So map.addLayer, water boundary data. Close brackets, we don't have any options. There aren't very many options for plotting vector data. That's one reason why it's kind of bad for making like professional grade maps, is the only option is color, is to change the color of the vector. So it's not very, we're just going to have these kind of gray blobs, unfortunately. All right, so I'm going to call this watersheds. So go ahead and click Run. If you're zoomed all the way in, make sure you zoom out to the US, because this is a US scale data set. All right. We've got all, or will have all, once this last tile loads. There we go. Oh. Okay. Now, you can use the inspector to actually figure out what the name of any of these watersheds are. So go ahead and grab the inspector and go ahead and click on any watershed you want. It'll drop down, it'll say watershed, you found one feature, and look in the properties, and it'll tell you what the name is. So go ahead, find any watershed, find whichever watershed you want. I haven't tested this tutorial on every single watershed, so there might be a little weird things on some of them when you're looking at them, but feel free to try. Go ahead and look at any one that you want, and then copy that name, copy whatever name that is over there, because we're going to use that in a minute. Okay. All right. So now we want to filter down our watershed. One thing, we don't want to plot all these. You only want to plot the one that you have. So what we're going to do, the fourth argument to adding something to the map is whether or not it's visible by default. We're going to say false. That means it'll still show up in the layer manager, but it won't be visible. It won't be, it's as though it started unchecked. So we're just going to keep it around in case we want to see this map, but we're going to hide it because we're going to only want to visualize the one watershed that we picked. Okay, so let's see. I'm going to define another variable called watershed, and we're going to take our big feature collection, and we're going to apply a metadata filter to it. Metadata. So this takes 3 arguments. The first one is which property you're doing, and we're doing the name property. If you look, you get it from here. If you wanted to do, for example, if you wanted to do area acres, if you want to do some kind of size filter, you would do this one up here. But we want to filter by name. Then the second one is what thing to apply. We're doing an equals filter because we want it to be exactly that name. And then I'm going to use the one that's in the example, but copy and paste the name of your watershed here. So the one in the example is the Republican basin. Don't worry, it's just a water basin, not the political party. All right, and then go print your watershed to make sure that you grabbed the one that you want. Oops. Go back over there. You should have. It should say it's still a feature collection, because when you filter a feature collection, even if you get it down to a single feature, same thing with an image collection, it'll still be an image collection until you tell it that it's just an image. That's why in the last example we had to say ee.image of the thing, because after all that filtering and sorting and taking the first, it's still technically an image collection, and we wanted it just to be an image. That distinction will be more important a little later. Okay, so now if you've printed it, check out the properties and make sure that the name, find the feature first, the one feature. It should only have one feature. Find the feature and check out the properties, and make sure that that name is the one that you did. Okay, everybody's got just the one watershed, and it's the one that they wanted. All right, everybody's good? All right, let's add it to the map. And now you can really see if it's the one that you wanted. Let's see. First, we are going to do map.center object watershed. So that's the object we want. And then the second one is the zoom level, how zoomed in and out you are. So we're going to put that. That'll just zoom us into the watershed that we want automatically when we run the code. That's just a nice little feature to do. And then we are going to do that add layer again. We're going to add watershed. We want no visualization parameters. And we're going to call it watershed. Go ahead and click run. And it should zoom in on your watershed and plot it. All right. If you got an empty feature collection, that probably means that you misspelled the name, or there's something wrong with the name, or something wrong with your filter that made it filter out everything instead of everything except the one that you wanted. So that's something to check if your feature collection is empty. Oh, and as a note, I didn't mention this. This data set classifies the Great Lakes also as their own watersheds. Don't pick those because we're looking at vegetation, and there's very little vegetation on the Great Lakes. So just a little note about this example here. Okay. Has everybody kind of found their watershed and got it plotted? Okay. All right. So now we want to grab all of the Landsat. Now we're going to grab all the Landsat imagery and filter it over our bounds and filter it by time. So let's go back to the code editor. We are going to make a variable L8 collection. Remember, that is an image collection. And this time, we're going to use a slightly different product. Don't really worry too much about the distinction for right now. If you want to know more, I'd be happy to talk about it offline. But we're going to use the Landsat 8 surface reflectance tier 1 product. So Landsat 8 surface reflectance tier 1. That's the one that we want. So go ahead and click on that, and the name is over here on the right. It's the same kind of layout as the top of Atmosphere product. And you'll notice a thing about the documentation. There's a lot of links, and really good the ones have a lot of links that you can click on. You can see how the product was made. There's sometimes reference papers in here. So there's sometimes a lot of really helpful stuff in the documentation. So if you're using a product and for the first time, go read the documentation for it before you start doing things, so you have a better understanding of exactly what it is. Okay, so we're going to grab that name. Go ahead and copy the image collection ID. You can put it in here. If you can't find it in the search bar for some reason, you can grab this off of the website, the tutorial website. The code for this is there. So we've got this. And now we want to filter the bounds by our watershed. So now we have only images over our watershed. And then we're going to apply another filter. We're going to filter the date. And we want to do we're going to do 2017 for this one. Feel free to do any time period since, let's see, when did, since 2014. Feel free to do any year that you want. Let's see, 2017, 12, oops, 31. Okay, and now we just have images over our basin and filtered by this date. Now note, this gives us all images that intersect with our basin. So you might have images that where only the small corner intersects with your basin, but it still intersects with it, so that it will use that, which can be sometimes a little bit annoying if you have an image that is entirely within one tile, but partially within the next tile over, so that you get all of the full images, which is what you want, and then you get the partial ones from the other one, which you might not want. You might not care about the partial observations of your region. So that's something that can be a little bit annoying, and that there are ways to get around that. But okay, so now we've got that. Let's print it and make sure that it is a reasonable size. Yeah. Yeah. Okay. So I've got 276 images. Yeah, 276 images. That seems like a reasonable number in a year. The satellite return comes every 16 days. This is kind of a long basin that I have. Depending on your geometry of your basin, you might have more, you might have less. But kind of in that ballpark. If you got like 3,000 images, then it's maybe a little bit fishy. If you only got 5 images, then that's maybe a little bit fishy too. But it should be kind of in this, hundreds of images kind of ballpark. And that's a reasonable amount to work with in Google Earth Engine. I believe it caps out at 5,000. If you have any collection greater than 5,000, it won't do anything with it. So that's kind of the upper limit. All right, so we have our collection. Okay. Yeah.
So here we're doing e-image collection. On the other script, we were doing e-image that we had 2 parentheses.
Yeah. So
here you close parentheses and it was still recognizing you're doing the filtering outside the parentheses.
yeah. So the reason for that is that dot filter is how you apply stuff to things. So for example, I put this on the same. This might make more sense if I put this on the same line. It's applying that to this collection. The reason then, so we had a bunch of those statements inside the parentheses of the image thing because we wanted to cast all that stuff that we had in there as a single image.
And it's because you didn't have the semicolons, that would have ended the line.
Right. So if I was being proper and using the semicolons, I would put the semicolon here and not up here or on that line. Okay. So a big problem with a big hurdle with using the satellite imagery is clouds, right? You can't see through the clouds. The clouds can't see through. Satellites can't see through the clouds to the land surface. So if you have clouds over your image, that part of the image is essentially useless if what you care about is the land surface beneath it. So we need to find a way to mask out the clouds. Now we could just go through all of the images and say throw out all of the ones that have greater than 10% that don't have 0 cloud cover. But then we might be throwing out a lot of good parts of images. There might be images where there's clouds in one part and not clouds in another part. And we want to use that cloud-free part of that image because it might be during peak growing season. And that's sort of what we're after. So we need to mask out the clouds. We need to find a way to get rid of all the pixels that have clouds and keep all of the pixels that don't have clouds. So we're going to write a function that applies a filter that does exactly this. It throws out all of the cloudy pixels and keeps all of the good pixels in the image. Now this would be easy. This is easy to do on a single image. It's really easy to do on a single image. However, for a collection, the stuff that we need to do it on an image, you can't just apply to a collection. It doesn't know how to do this to a collection. It doesn't know exactly what you want if you try to apply this to a collection. So we need to use a process called mapping. And I apologize for the syntax here. This is lowercase m mapping. I don't know why they did this when they have a big map and they have a bunch of things about adding stuff to the map. But the process we're going to be doing here is lowercase mapping. And it's like looping. It's essentially doing a for loop, or iterating over all of the images in your collection and applying some function that we wrote to each image in the collection individually. So that's what we're going to be doing. You want to avoid using like regular JavaScript loops at all cost, because those loops will then, it'll back out to your browser and do some stuff in your browser while it's doing the loops and have to send data back and forth a whole bunch, especially if you have like, a large collection. If you have, say, if you're iterating over a 500 element collection and you do this loop, it's going to have to send information back and forth 500 times and do this communication 500 times. Is that, yeah, that's something that everybody tries when they're learning Google Earth Engine, and they find that it's a bad idea. I did that a lot, and it doesn't work out. So we're going to use lowercase mapping to solve this problem. This makes it so the iteration takes place all in the cloud, goes by really quickly. So we want to mask out all cloud things. So we're going to first write our function. We write a function such that it can take any image. It takes an anonymous image from the collection, applies the mask, applies whatever we want to do to it, and then returns that image back after it's returned. And then if we apply that, if we put that in the map function, it will then apply that. It'll do that function to every image in the collection. So let's first write our function. So to make a function, you define it like a variable. You say we're going to call it mask clouds, and you say equal to function, and function should turn bold. And it's just going to be an anonymous image. We're going to do a function of image, and then you use these the open squiggly brackets. If you hit enter, it should automatically close the bracket on the next line below you. So now everything we do in here is inside the function. So the first thing we want to do is we want to pull out the pixel QA bands from this. These are the quality assurance bands. These bands have information about how cloudy each pixel is. So we're going to use these to inform us, to tell us which pixels have clouds and which pixels to get rid of. So we want to grab out just this band. So image.select. And the name of the band is Pixel QA. Now you can get that if you look in the documentation up here for the Landsat Surface product. Down here, there's this Pixel QA band. And it's actually in binary. So there's flags for all these different things. So there's a flag for, I'm not sure what the fill flag does, but there's a flag that says this is a clear. There's a flag that says this is a water. Then there's a bunch of flags for saying, cloud, shadow, snow, cloud, all this other stuff. A tricky thing with using these is, so this is in binary. When Google Earth Engine then calculates the value of it, it just converts it to decimal. So you do have to do a little bit conversion to figure out what your value are, what values you're looking for in these QA bands. If none of that made sense to you, don't worry. You can. I'm happy to talk more about that later. But just for now, we know, or I guess I know that the pixels that are clear end up having a value of 322, and the pixels that are water pixels have a value of 324. And those are the two values that we want to keep, because those are the two clear ones. Now, we are also throwing out the snow pixels, but since we care about the growing season, that's okay, because that's not going to be the peak growing season anyways, for what we're looking at least. Okay, so now we're going to define a new variable. Oh, no, we're not. We're actually just going to change our image. We're going to say image equals, and remember, this is the second time we're using it, so we don't have to define it. Image equals, let's see, image dot update mask. Now, update mask is how you mask things out of your images. It's how you throw out some pixels and keep other pixels in your image. So that's what we're going to be doing. Okay, I'm going to write out this kind of chunk of logic, and then we're going to unpack what it means. So stick with me for a second. So let's see, pixel QA dot equals 322. Oops. Dot or pixel QA dot 4. Okay, so let's unpack this little chunk of code from the inside. So if you just say, if this .eq, that's equals. It's a logical function. What it does is it looks in whatever image you're applying it to, and it says, any pixel that is equal to the value you give it, we'll set that value equal to 1. If it's not equal to that value, we'll set it equal to 0. So the result of that is just a map that's just ones and zeros. Ones where that equal is true, zeros where that equal is false. So we're saying, all right, if it equals 324, we'll make that 1. OK, and same thing over here with the 322. So we have these two masks of ones and zeros. This .or between them puts them over each other and says, OK, if they're both 1, we'll make the final result is 1. If either of them is 1, we'll make the final result 1. If they're both 0, we'll make it 0. So the result of this is a mask that is just ones and zeros, ones where where both of these conditions are true, where it's where either of the conditions are true. I mean, where if it's equal to 322 or 324, there will be a 1 in that pixel. Otherwise, the other pixels are 0. And then finally, if we give that to the update mask, what it does, oh, yeah. Hold on. Yeah, so that's just the value of that code, of the code that says, for 322, it says, that's the code for if the pixel is clear. 324 is the code if the pixel no, 324 is if the pixel has water in it. 322 is clear over land, 324 is clear over water. So those are the only ones we're worried about. If you want to know more about like where those numbers came from, I can talk about that a little later. For now, we're just going to like accept that that's what those mean. OK, so we've got this mask, and when we put it into update mask, it looks at image, the thing that we're updating the mask of, and it sets our mask over it. And anywhere where there's a 1, it keeps the image, and anywhere where there's a 0, it throws those pixels out. So essentially, what we'll get is an image with all of the cloudy pixels thrown out, and only the land and water pixels remain. OK, does anybody kind of have questions about how that little bit of logic works? I know that's kind of a complex line to unpack. OK. All right, and the last thing we need to do in our function is we need to return our image. So that means that this function takes in an image and takes in the image, does some stuff to it, and then returns it. That's sort of the format for any kind of mapping operation. Is you want to write a function, takes in an image, does some stuff to it, and returns an image. OK, and now we are going to apply that to all of our images. So we're going to define a new variable. I'm going to call it L8 masked, and that is equal to our L8 collection dot map. This is where that dot lowercase map comes in. Whenever you see a lowercase m, it just means you're mapping something over a collection. Capital M map means you're adding something to the actual the map that's right below you. OK, and then we just give it the name of our function. Oops. Mask clouds. All right, so now we've masked out all of the clouds. Let's check that. Let's add a non-cloudy or a pre-masked and a post-masked image to our map down here. So first, we're going to define some visualization parameters so we don't have to keep typing in the same stuff over and over again. So I'm going to call this visparams, and we put this in the squiggly brackets here. Bands. So bands is the first thing we're going to define. We want true color. It's the same stuff as before, essentially. Band 3 and band 2. And then we're going to define a minimum. You might want to play around with these depending on where your basin is and how bright and reflective it is. These are good parameters for this basin, but you can play around with them. Note that the band values in this are multiplied by like 10,000 compared to the band values of the product that we used last time. So that's why last time it was 0.5, and this time it's like in the thousands. So our maximum, we're going to say 2,000. All right, that should give us a decent I'm going to go down a little bit, a decent visualization. So now let's go ahead and add some stuff to the map. Add layer. This is where we're going to be casting something as an image. We're just going to take the first one off of both. So this L8 masked, my bad. So we're just taking, what this does is it just pulls the first image off the collection, and then we tell Earth Engine to treat this as an image and not an image collection. So let's see, yeah. And then we're going to put in our viz params there. And then we're going to call this cloud masked. Okay, and we're going to do the same thing for the original collection. Image 8 collection dot first. Viz params, and then we're going to call this original. Now I suspect that some of you, your first image might actually be cloud free, so for some of you this might be kind of disappointing. You might just get the same image twice. But for others, when you go to click run, let's see what we get here. Should get, okay, so I got a really cloudy or snowy image at first, I guess. And then you can go into the layer manager and turn off the original and see what was left after your filter went through it. Here, not much. You can see there's a few dots that are around, but not much remained of this initial one. Probably because I imagine a lot of this is just snow, because it is the first image if you're filtering by a year, it'll just grab one from January. So I'm guessing this is probably a lot of snow that we filtered out. Did anybody else have kind of success? Did you see like a cloudy image or a snowy image and a lot of it got obliterated? All the snow or clouds left and your final thing is just some pixels? Let me see. If you're getting a lot of black, if your image looks dark, decrease the minimum. Decrease the minimum and the maximum, and you'll get, So if your image looks too bright, you can try, if you increase both the minimum and maximum, if the image looks too dark, try decreasing those to get a little bit better looking image. What? Oh, yeah, sorry. There we go. Yeah, if it's too bright, then increase both the minimum and maximum. Yeah. Yeah. How the visualization parameters, how they work is if any pixel value is at or above the maximum that you set, it will set that as the brightest possible pixel. If any pixel is below below the minimum, it'll set that pixel as the darkest. So that'll be like a black pixel, and above will be like a really bright white pixel. So if you adjust that range so to make sure that more of your pixels are inside the range instead of outside the range. You'll get a better looking image. Let's see. Okay. So I think we're like 5 minutes away from lunch, right? Okay. So I'm just going to introduce a concept. We're gonna walk away from the code editor for a second. I'm gonna introduce a concept and then save this code. We're coming back to this after lunch. So go ahead and click save. Make sure that it's saved. Okay. I'm gonna go back to our the tutorial layout, and we're gonna talk about normalized difference index real quickly. Oh yeah. Okay. Yeah.
I sort of played with this number, maximum and minimum. I got something like that.
I think it's also because of the bands that you're looking at. Yeah.
Is it for this area particularly, or is zooming from a segment of this watershed coming out and showing me somehow?
No, it's from where it shows on the map. Yeah. Okay. So we're going to talk about normalized difference index. So this is a very common tool used to analyze satellite imagery. So what it does is it's just a measure of the difference between how bright two different bands are. And depending on which bands you pick, you can isolate certain different phenomenons. The reason it's normalized difference because you also divide by the sum of the brightness of the two bands, so that you end up with a value that's between -1 and 1. And depending on which two bands you use, it highlights different features. So we're going to be looking at the normalized difference vegetation index here, which is used to highlight vegetation. So how it works, vegetation leaves they absorb a lot of red light. So they just suck in all of the red light. They reflect very little red light. They hold on to that. So the amount of red light that comes back to the satellite is very, very little from leafy areas. In contrast, they really reflect near infrared. Near infrared just bounces off like crazy. So you have a really high near infrared brightness at the satellite. So in an image, if you calculate this normalized difference index over the entire image, vegetation shows up really bright. You see it really stands out compared to, say, land surface or water, which is actually the opposite. Water really absorbs near infrared, reflects a lot of red. So water actually ends up being a negative NDVI value. There are many variations on these normalized difference indices that are targeting different features. So this is one way that you can take kind of a complex data set, and this is one way of reducing your amount of data down to something that's manageable and useful for kind of identifying how vegetated an area is. So when you come back, we are going to look through that. We are going to calculate the NDVI. We're going to map it through the entire image collection that we just made. And then we are going to reduce that entire image collection set down to the maximum NDVI and look at the maximum, kind of the maximum extent of vegetation across our basin. So that's what we're going to do when we come back. So well, we're probably waiting on a few people to filter in for lunch. But remember, we are going back to this Access Satellite Imagery tutorial. I guess before we begin, did anybody have any kind of questions that they might have thought of during lunch? Anything that came to you? Turn my slide. No? Okay. So remember, we were right in the middle of this tutorial. We just learned about the normalized difference vegetation index. And now we're going to be calculating that for all of our Landsat image collection that we've filtered and masked out all the clouds. So go back, open up your script, make sure that it's still there, find the script that we were working on. I think the last thing we did was print that, add the cloud masked image and an original image just to see if the cloud masking worked, and it seemed like it worked for most people. So why don't you, I'll give you a minute to just bring up your script, make sure it's still working, make sure it's still all there. If it's not, reminder, at the top of every tutorial, there's a link to all of the code in the tutorial. So you can just grab that and then just delete everything up to where you were if you want to go through the tutorial yourself. That's another way you can get back to where you were. OK. Any problems, I guess, recovering your script from where it got saved in Google Earth Engine? OK, so let's get going. So we're going to do the exact same process that we did for masking clouds for calculating the NDVI. The same kind of, we define a function that calculates the NDVI and returns it into the image and returns the image. Let's do that. Let's start. Let's define a variable. This is going to be our function, get NDVI. That equals function of an image, just a generic image. And let's see. Now this is very simple. It's just a single line of code. We're going to return it. We're going to turn this. We want the same image because we want all of the original bands that came with it. We just want some extra stuff with it too. So we're going to say image dot add bands. So that will return whatever we, not double dot, my mistake. Dot add, and B should be capitalized. Yeah. Add bands. And then, so what this will do is any image that's, whatever image we give it, it'll add that image as a band to the original image there. So we are going to say image dot normalized difference. This is actually such a common thing to use. The Google Earth Engine has a built-in function to do this arithmetic equation here. You can go through and do it code it up the manual way. Do like this band minus that band divided by that band plus that band. And there's a way on the website. It shows you kind of how you would do that. But we have this, so we don't need to do anything fancy like that. So we're just going to say, you just put in the first band and then the second band. 5 is the near infrared. 4 is the red band for Landsat 8. And then after we've calculated that, we need to add a little something extra. We need to rename it. We're going to rename it to NDVI. Whenever you do an operation like normalized difference or even addition and subtraction or multiplication or something, sometimes it changes the name of that band. And if you don't rename it when you make it, you don't know what the name is. It gives it some generic name, and I always forget what the generic names are. So I always do a rename of that band so I know what the band is called later on when I want to use it. And that's it. That's how you calculate NDVI of a single image. And now we map that image across the collection. So we're going to define a new variable, var L8 NDVI equals L8 masked, and it's just the dot map get NDVI. And that'll do it. And now let's just print. Nicolette, it says that my audio is very low on the recording software. Your primary audio source is very silent or quiet. This is on because it's, yeah.
Try using this one.
Oh. Let's see. How about this? Does this? Standard AV bridge. Yeah. I'm not sure why it's doing that. Why it's saying that the audio is low. I don't remember if there was any kind of feedback here on the audio.
Should be working.
Yeah, I guess so. Okay.
Thanks.
That's fine. All right. Oh yes. So now we're just to make sure that our map worked. We're just going to print the first one. We're just going to print the first L8 NDVI dot first, just to make sure that it is how we said it was. So that's this one down here. Set 8, so it's still a Landsat image, but now it's got 13 bands, and at the end here you'll see it's got that NDVI band. So all we did is we returned the same image, but we gave it an extra band with this NDVI that we calculated. So excellent. That's what we wanted to do. Did everybody kind of get there? Does everybody in there printed, or are there errors that people are running into? Authorization token. Let me take a look. That might be something that I should talk about. Cannot perform analysis without authorization. Okay, when you have that, save your script. Make sure that just, let's see. Okay, now refresh the page. Sometimes, did you put your computer to sleep and then, yes. Sometimes when you put your computer to sleep and if you open it up and are on the same tab, sometimes Google Earth Engine, you'll be in Earth Engine, you can view your scripts and save stuff there, but you lose whatever you need to actually connect to the server and run stuff. So you just need to refresh when that happens. Okay, so now that we've calculated NDVI for all of our images. So now we need to find a way to remember our goal is to find the maximum vegetation. What's the peak growing season? What does this basin look like at the peak growing season? So now we are going to apply something called a reducer to our image collection. Reducers, as they imply, they reduce the amount of data that you have. We're going to be applying a temporal reducer. What that does is you can think of your image collection as a stack of these Landsat images on top of each other. And it's a stack through time. They're all taken at different times. And what we're going to be doing, what a temporal reducer does is it looks at every location, so at every grid cell, there's a stack of grid cells beneath it. And it looks at all these grid cells and it reduces them to a single value. It reduces the value in all those grid cells down to a single value based on whatever method you tell it to. That can be, maximum. It could find the maximum value. It could find the minimum value. It could do the median, the mean. There's a whole bunch of different types of reducers a way to reduce this. So what this does is it collapses our sort of three-dimensional time series of data down into a single flat image. So it's a lot easier to interpret and understand. So we're going to be performing a special kind of reducer called a quality mosaic. Now what this does is you tell it which band you want to reduce it on. We're going to reduce on the NDVI. It finds the maximum. It looks through that whole stack of images for every pixel and finds the maximum NDVI. And when that occurred, it's going to grab all of the other bands that are attached to that were taken at that time and return those too. So it's kind of like a maximum reducer, except there's a little bit, except we're only taking the maximum of the NDVI and then keeping all the other bands the same at that time when it was reduced. Okay, so to do that, it's as simple as we're going to do a new variable. Composite is what we're going to call this. We take our L8 NDVI and we do dot quality mosaic. And then we just tell it which band we want it to base off of. And then with our output, we don't really care about anything that's outside of our basin. We only want the stuff that's in our basin. So we're going to do dot clip watershed. This will clip all of the output to the bounds of your watershed, so it looks nicer and it's easier to understand. So let's go ahead and let's print this so we see what we've got. Yeah, let's just run that and print it just to make sure that it's computing fine. So you'll see at the end, you should end up with just an image. That's 13 bands. Note that it's lost all of its metadata because it doesn't aggregate any of the metadata from all of the images that it put in there. You just lose all the metadata. It's just a blank image with these 13 bands that are just the product of that reduction that we did. far, so good. All right, and now we want to we finally can visualize this big data set that we reduced down. We're going to visualize it. But we're going to use a very particular palette. Now, you don't have to do this, so you can just leave this out. But if you go to the website, you find this chunk of code that says NDVI palette. All this is it's just a bunch of different values. All of these are just a bunch of different color codes, mostly just shades of green for displaying this vegetation data. So go ahead and just grab that whole chunk and copy that and put it into your code editor. If you can skip this and you can just get a black and white image that'll still kind of tell you the story, but this just looks a little bit nicer. Okay, so now we're going to say map.add layer, the composite, and we only want the NDVI band. So we're doing a dot select here. And then let's see. Oops. Right there. And now we are going to put in our parameters. Minimum 0, max 1, palette, NDVI palette. And then we're just going to call this NDVI so we know which band this is. Okay, so then go ahead and try to run this. And you'll see, you get your sample images will be there. I'm going to get rid of those. Oh, I did something wrong with my palette, I think, because I just got a black and white image. Ah, thank you. And is that right? There we go. Okay, so now you should have a map that looks various shades of green. Oh, I'll bring my code back. There we go. Various shades of green of your own basin. Did that kind of work out for everybody, or? Did anybody see anything cool in their basin? Anything interesting? Okay. And the last thing we're going to do in this example, there's more to this example on the website, and you can follow through on that later on if you want. We're going to add the original color composite, or the true color composite to this as well, just to see. Yeah. Oh, a legend. That's another thing why why Google Earth Engine is not particularly good for cartography, because there is no legend support. Legends have to be made manually, which is not very fun. There is an example of legends in the examples to how to make one and how to make the values that I've sort of copied and adjusted, but it is a very manual approach. It's a very much adding a box to the map, adding smaller boxes with the colors that you want. So it's so the support for making a legend is not really there, which is unfortunate, but yeah. Okay, so the last thing we're going to do is we're going to add in our color composite. So put composite back in there. We're going to add map.addLayer. And now we got to select our bands, or which bands we're going to do. We want bands, before 3 and B2. And then we want a minimum of 0 and a max of 2,000. And again, those values might change for your basin depending on how bright or not it is. Okay. And I'm going to call this true color composite. Oops. Loads, and then you should have this kind of true color composite that's sort of represents what visually what the basin looked like when at this maximum point of NDVI. But remember, you're also when we did this big reduction, we also lost all information about what time all of these events, like this maximum NDVI, occurred. So whenever you do a reduction, you do lose a lot of information. And doing a reduction is all about deciding which data you're okay with losing and which data you want to isolate. So here we just really wanted the peak growing season. We didn't really care when it occurred at this point. So we do this kind of maximum reduction. Okay. Were there any questions? Does this work for your basin? Are there any kind of questions, maybe conceptual ones about how this works, how the reduction works? Yeah.
Caveat, I'm not actually following along.
That's fine.
I have a broader question. Again.
Yeah.
I realize that in this case, as you said, you're using a convenience function for that reduction, the
Yeah.
maximum NDVI.
Right.
And you lose metadata. So convenience versus something you lose. Are there ways in Google Earth Engine to write your own reducer, if you will, so that the metadata gets preserved and we can take advantage of that?
Well, so when you do the reducer, right, you have a bunch of images, you're reducing down to a single image. So you can do something to grab the metadata from all those stuff and aggregate it in such a way that makes sense to you. Yeah. Some of it, it obviously on an individual property level on what makes sense. So there's that aspect of it. In terms of doing things like for example, if you're interested in the timing, when did this happen? A temporal reducer is probably not what you want to do because you've reduced the temporal dimension entirely. It's gone. There's another type of reducer called a spatial reducer, which we'll talk about a little bit more. So I'm not going to get into it here. And that's used a lot in making time series, which we're also going to do next. So you can also, another way to reduce it is spatial reducers reduce an image over a region into a single value. So then if you can then plot those values in a way that makes sense.
Are you saying then that for the temporal reducers,
yeah.
there is no convenient way or not too troublesome way to bring in the time metadata
yeah.
Not just one line, but
it's a little inconvenient. There's a way. There might be a smarter way that I'm not aware of, but you can make bands. So you can make a band where all the values are equal to the date. Yeah. And then when you do your reduction, it will hold. If you do, for example, this quality mosaic, if you had a date band in all of those, that pixel would be the day that pixel was maximum. So there are ways around it. It's not convenient. But yeah, so there's a lot you can do there. There's a lot of information there's a surprising amount of information you can store by just saving that value as a flat band in your data. Yeah. Okay. Are there any more questions about this example? All right. I think we're going to move on. So let's look at let's go back to the website and let's go back to the main page here. So there are a lot more tutorials here than is even possible to get through in a day, maybe even a week. So these tutorials are all here. Everything is written out and explained, and all of the code is all there. So a lot of these the ones we don't get to, you can explore at your leisure and look through. We are just going to skip right to the SAR water body classification tutorial. And so that's what we're going to do. You can feel free to go back and look at the temporal and spatial reducers, the time series, and there's also a bonus supervised classification one at the end there. So feel free to do those at your own leisure. All the code is there. The sample code is at the top of all of them. All these tutorials are designed to work without me up here talking at you about them. You can just read through them and do them that way. Okay. So everybody go to that SAR water body classification one. So we just had to go to some great lengths to deal with the issue of cloud cover ruining our satellite images. We had to mask out all those pixels and do those reductions. Well, and that was fine because we just wanted the maximum at some maximum value over a year. And we're assuming there's enough cloud-free images over our region for that year to get that maximum. But what if you're interested in, say, a time series, how the land surface is changing over time on shorter time scales than a year? Like, let's say you wanted a monthly or sub-monthly time scale of how things are changing. You need to be able to see through the clouds. And in some regions, that's not such a big deal. Other places, like here in Washington, where we have a cloudy season for 6 months of the year, or places like South Asia, where they have monsoon for 6 months of the year, where you're just not really going to get much data out of there. You need to have some kind of other method. One way is you can leverage, because Landsat has been taking pictures of the Earth since the mid-'80s. So you have this long time series of Landsat data, and in there somewhere you might be able to find an image of during that cloudy season of the land surface, kind of a rare image, and you might be able to piece together whatever you're looking for based on that. But another way is to turn to a different type of data. So here we're going to be looking at SAR data, synthetic aperture radar. This SAR radar penetrates clouds. It goes right through the clouds. So cloudy days, we don't really care. Some sensors are a little bit iffy in really heavy rain, but we're not going to worry about that right now. So it goes right through the clouds, and we can see exactly what's happening underneath. We get a more continuous time series of what's going on. And in this example, we're going to be using this SAR to look at how a new reservoir in the Mekong River Basin in Southeast Asia, we're going to look at how a new reservoir that was put in, we're going to watch it fill up, and we're going to see how it operates and see what happens with it. So a quick thing about how SAR works. So SAR sends out a radar signal. It's not like Landsat that's just kind of looking down at the reflected light back. It's actually sending out a radar signal, and it sends this signal out off nadir. That means it's not looking straight down. It's looking kind of off at an angle at the land surface. And that signal goes down to the land surface and breaks apart. Some of it just reflects off and goes away from the satellite. Some of it it scatters and sends a signal in all directions, and then the amount that scatters back right at the direction of the satellite is how much the satellite measures. The amount of scattering depends on how rough the surface is. So really rough surfaces scatter a lot. You have really high backscatter coming back to the satellite. Really smooth surfaces, like water, don't really scatter at all. They tend to just reflect like giant mirrors. So and because we're looking down at an off angle, that beam just goes away. And so you have a really, really low backscatter back to SAR. So we can use that to leverage, we can use that contrast to identify where the water is in an image and classify how that water changes over time. So that's what we're going to be doing. It's a very surface level introduction to SAR. It's a tricky thing. That's kind of the very basics of what we're going to be doing here. Okay, so I have a very specific region for you to look at. You can later on move this polygon around to different places and see how things work. It's not a foolproof code, I should add that. It might break if you move the polygon around, but we're looking at this very, very specific region in Southeast Asia. So I want you to go to that website and just kind of grab this place where I define the geometry, copy all that, and put it into a new code. a new script. We're going to ignore that. Okay. And then let's click run and make sure that it is all copied over. You should have this kind of weird little polygon over here in Southeast Asia. Okay. That worked for everybody, right? That was okay? Okay. Let's see. Okay, so now we're going to load some SAR data. And the specific SAR data we're going to be looking at is Sentinel-1, which is a European satellite launched in like 2013, 2014, 2015, somewhere in that range. And it is, I think it's the only publicly available SAR data set in Google Earth Engine, but I'm not 100% on that anymore. So yeah, let's load it up. So let's search for. Oops, I can't spell. Sentinel-1. What am I? Oh, I see. Okay. Sentinel-1 is right here. Note on Sentinel-2, that's like a European version of Landsat that launched fairly recently. So that's another version of satellite imagery that you can use if you want to. But we're using Sentinel-1. So go here and grab the code. You can take a look at what bands are available, but I'll kind of describe that. It's a little bit tricky. I'll describe that a little bit once we've copied it and take a look at it. So go ahead and grab that Sentinel-1 name. Okay, and we're going to put it in here. What did I do? Oh, image collection, and put that name in there. Okay. For everybody just joining us, we just started the Sentinel, the SAR water body classification. And what I'm going to do is I'm actually going to get you the link to what we've done. All we've done so far is load a polygon and load some SAR data. So I'm actually going to get the link and start you off from exactly where we are, and I'm going to post it in the Waterhackweek general. Oops, that's not the link. Okay, this is the link. Okay, so you should all be able to open that, and you will see kind of exactly this.
Can you show again how you get the link?
Oh, yeah. Yeah, you click on link, and it changes your URL to whatever the link is. So I'll give the people who just showed up a few moments to get that going. Okay. Does that link work? Did you? Awesome. Excellent. Okay. Okay. So now that we have our SAR data loaded, we are going to filter bounds to our region. I named the region ROI, region of interest. I didn't want to give it a specific name. Just in case you want to move the polygon around, if I call it, a specific name reservoir and you move the polygon somewhere else, the name might not make sense. So I just named it the generic region of interest. So we're filtering bounds over our region of interest. We're going to filter the date, and we are interested in from 2017 through present. So 2017, 01, 01, and you can just say, I'm just going to say 2020-0101. It'll just filter out. There's no images that far ahead, so it doesn't really matter. Let's see. And then there's one more filter we have to apply, and this is kind of specific to looking at SAR data. So SAR also collects, when it collects the data, the backscatter that comes back, it collects it in different polarizations. So essentially which way the, you can kind of think of it of which way the light is vibrating. So it sends out the radar signal vibrating vertically, and then some amount of it comes back vertically, and some amount of it comes back polarized horizontally. So it's the same thing that makes your 3D glasses work in movies, the different polarization. So, and we're after a very specific polarization. We want only the vertical, the stuff that was transmitted vertically and returned vertically. You can use the vertical and then horizontal return one for this. There's just some different thresholds. But we're only interested in the VV. So, and we want to make sure, because this specific instrument collects and receives in different in different modes. So some of the images will be unusable if we don't do this little filter here. So we're going to make a generic filter. So that's just the dot filter. And then to do that, we need to, the arguments for making a generic filter is you have to make a filter object. And you can see what all the different filter objects are in docs. There's actually ee.filter, and it has all of the different kinds of filters. Note this, for example, ee.filter.date is the exact same thing as filter date, filter date that we just did. So we are going to be doing a .list contains filter. And then there's this long, let's see, I'm going to type it out. You can just copy and paste from the thing if that's easier for you. Transmitter, receiver, polarization. Oh, and that should be in quotes like that. And then we want to make sure that it contains the vertical one. So I think I spelled that right. Nope. Yep, yeah. Okay. All right, so now we've filtered over our collection. We've looked at the entire Sentinel-1 SAR archive. We've got all the ones that are only over our region, only from 2017 onward, and only ones that are in the right mode to have this VV band. Okay, so let's just add the first image to see, what this data even looks like. So we're going to do map.add layer s1.first. And the bands that we only want the VV band. Minimum is going to be -18, and the maximum is 0. The way that they measure backscatter, all of these values are going to be negative. Let's see. And then we're just going to call this SAR image. Okay, so let's go ahead and run this and see what we get. Should get something that looks like that. Now, the water body that we're interested in the dam hasn't been built yet, so the reservoir doesn't exist at the beginning of 2017. So that's why there's seemingly nothing in the region that we're interested in. But you can zoom around and look at other water bodies and notice how dark they are compared to the land around them. And that's the property that we're going to leverage to classify the water bodies here. Okay, did everybody get that far? Is everybody able to load this SAR image? Oh, back to the code, yeah, sorry. There. Oh, yeah. Okay. All right. So let's look around at some of these. If you look around and zoom in on some of these water bodies, one thing you'll notice, if you zoom in a little bit close, you'll notice that there's a lot of speckles. Right? It's sort of grainy, like an old film. And that's just something, or at least what I think it is something when the signal comes back to the satellite, something interfered with it. You get some kind of interference, some kind of atmospheric interference. It could be something else. So you get all these little speckles, all these kind of random speckled noise. And if we go to classify this image right now without taking care of the speckles, some of those speckles we might think that they're land because they're bright. They're a lot brighter than the water. So we need to do something to minimize this speckle noise. And there's a lot of techniques to do this. There's a lot of different methods. There's a lot of really complex methods. We're going to do a really, really simple one. So it does not perform as well as the best one. So keep that in mind, that we're not going to get all the speckles. And there's some issues with this one, but it's still good enough for what we're trying to do here. So, and it's the same thing. We're going to be mapping a function over our collection that does these speckles. So I'm going to call this, I'm going to define a variable called filter speckles. Speckles. Equals a function of our generic SAR image. We're just going to select the VV band. Dot select VV. I'll make this bigger. Okay. And then we're going to define a new variable, which is we're going to call VV smoothed, because what our filter is going to do is it's going to smooth the image out. So when in smoothing it out, we will get rid of all those we'll get rid of a lot of those speckles. So we're going to say VV dot focal median. I'm going to put in the arguments here, and then I'm going to explain them. So it's 100 circle, and then meters. Okay, so what the focal median does is it's kind of like a reducer. It looks pixel by pixel, and at each pixel, it looks in a 100-meter radius, a 100-meter circle radius around that pixel, and it takes the median value of all the pixels around it and puts it there. So in doing so, right, the speckles are in the middle of water, so it'll look at all the water and grab the median value and get rid of the speckles. That's the idea behind it. And at the end here, we are going to rename it VV filtered. So that's what just so we remember what the band is called. And then we are going to return the original image, and we're just going to add this band to it. VV smooth. Okay, and then we just go through and map that function. Oops, every time. Okay, so now let's see what the smoothed image looks like in comparison. Let's see what changed. So, oops, capital map.addLayer. S1 dot first. We're just going to grab that first image again, but this time our bands are going to be VV filtered. Oops. And we want the same minimum and maximum. And then I'm going to call this our filtered SAR image. Once you've got that, go ahead and run it. I'll bring the code back. Let's see. There we go. Oops. I flipped my minimum and maximum there. That's my mistake. -18 and 0. It's interesting, though, that it inverted the colors on I thought that nothing would happen if you set maximum greater than minimum. Okay, so now we've got these two images over the top of each other. Let's see. Yeah, there we go. Okay, so try zooming into water body. Notice we didn't get rid of all of the speckles, and you'll see how it kind of got duller. It seems like we kind of lost a little bit of our resolution. That's because we smoothed this thing out over big 100-meter circles. But we got rid of enough of the speckles. This isn't the water. If we were looking at this water body, we might need to do something a little bit better to get rid of all of those speckles that are up here. But for the one we're looking at, it's going to be pretty good. Was everybody able to get there? Did everybody get that smoothed image? Did that work out? Cool. All right. So now we're going to have to map it. Now we get to where we want to classify the water. That is, we want to make a band for each of these images that just says 1 if it's water, 0 if it's not. So again, we're going to be writing a function and then mapping it over the collection. Okay. So we're going to call this classify water. And it's a function of a generic image. We want to get out that smoothed VV band. So we're going to do image.select .select filtered. Okay, and now we're going to use a really simple criteria for classifying the water. We're just going to set an arbitrary threshold and say everything darker than that, let's just assume that's water. This is like the bare minimum. This is like the most basic way you can do this. There are other techniques with SAR that get very complex, but I didn't want to bring that into here today because it might be pretty confusing. So we're just using this really simple threshold. So there are going to be errors associated with this, associated with our choice of threshold. But the overall patterns that we see in water change we're at least going to be able to see the patterns in water change, is my point. And that's all that we're after right now. So we are just going to say anything lower than -16, let's just say that's water. Let's just call that water, everything greater than that. And so we're going to make a new variable called water. And we're just going to take VV, and to do less than, it's just LT. LT -16. What that does is now makes a mask, where all the water is, everything that meets that qualification is 1, everything that doesn't is 0. And now, because we did this thing, we want to rename it so we know what it is called. And I'm just going to call this water. All right. And now we're going to do something. We're going to actually throw out all of the pixels that are equal to 0. We just don't care about them. This is purely for mapping purposes. We just want to get rid of those pixels, kind of in the same way that we got rid of all of those cloud pixels. So to do that, we're just going to say water equals water.update mask with water. If you update the mask of something with itself, it just throws out all pixels that are equal to 0, which is a neat little trick, something useful also for visualizing precipitation. You don't really care where the 0 precipitation is. When you look at a forecast map on your local news, they don't have there's no color for the 0 precipitation. It's just see-through. So this is how you would get that same kind of visualization. It's to mask it with itself and throw out all those 0 values. Okay, and now we're ready to return this image. So image.addBands, water. Okay, so let's map that over our collection. Classify water. And let's print the collection to make sure that it does actually have that water classification that we wanted. should have something with about this many elements. Let's look at the features, and let's just pull out the first one and make sure that it does indeed have that water band that we were after, that water classification. All right, did that work for everybody? Yeah. Oh, go to the layer manager. Let's see, and let's look at the top one. Click on the gear, yeah. See, because what it's doing is it's making a 3-color composite. So you just want one, yeah. Apply, yeah. Yeah, so what happened was when you added it to the map, you didn't specify which bands you wanted. So that's if you just add something to the map that has more than 3 bands, it will assume that you want a 3-band composite, even if that doesn't make sense at all. That's how it will plot by default. Okay, so now we have this time series stack of images, of classified water images, and we want to know how much water there was. We want to see this time series, but we don't need to. There's no image that we can get. We're not going to reduce this down to an image. We're not doing a temporal reducer. We're going to do a spatial reducer on every image in the thing to calculate how much water area there is in each image. Now, you can write a function that does a spatial reducer on an image and then map that over your function, but there's kind of a shortcut to getting this, and that is making a plot. Because at the end, you still want to visualize your data, and you want to see it. So we might as well just make a plot, and that has kind of built-in this kind of built-in reduction, spatial reduction time series feature in it. So we are going to go make a time series plot. So we are going to make a new variable. This is going to be for our chart. I am going to call this class chart. And now there's this long kind of command to get the right chart that you want. So it's a UI dot chart dot image dot series. There are all kinds of different little charts, and you can find them under the UI.chart option in the docs, and you can see what all your other options are. But this is the one we're using here. And for the inputs, I'm going to put all the inputs kind of in a line because there's a lot of arguments here. So for the arguments, the first thing it needs is an image collection. And the image collection we want to give it is our S1, and we only care about the water band. So we want to .select water on that. And then we need to give it a region. We need to tell it what region to do this reduction over. And that's going to be just our region of interest, our ROI. And then we need to tell it how we want to do the reduction. And this is where we need to tell it which reducer we want to do. And to find which reducers you want, what your options for a reducer are, you go to the docs and you can see in reducer, these are all the different types of reducers you can do. And some of them I do not understand what they do, but other ones make more sense. Like first, that just pulls the first one off. It's the same as the .first thing that we did. There's count. That'll just take the count of whatever values you're giving it. Anyway, so we're going to give it a sum reducer, because what this is going to do is it's going to count all of the water pixels that we defined and tell us how many water pixels there are. And if we wanted the total water surface area, we just multiply that by the pixel size. So that's our reducer there. And then we are going to, now we have to tell it what scale it is. And now this is a bit of a tricky thing with Google Earth Engine. Whenever you do a process, it's not actually doing that process at the natural grid size, the natural resolution of your image, unless you tell it to. For most things, like making a map, it doesn't matter. Because if you're so zoomed out that you can't see the individual pixels, it doesn't really matter. So Google is actually being pretty lazy, and they're doing as few processes as they can to give you your desired output. But for things like spatial or temporal reducers, it doesn't really matter. For adding things to the map, it matters. But when you're averaging over space, it matters how big your pixels are. So we have to tell it how big the pixels are. You can actually tell it whatever size you want. Our pixels here are 10 meters. If you put in 10 meters, it's going to take kind of a little long time to run. You can try it and see. We're going to up it to 100 meters just so that it averages the cells to 100 meters and then it does this and then does our reducer. You can try it at 10 meters and see what kind of difference it makes in your numbers. I haven't found that it makes too big a difference here, but in general, you want to stick to your native resolution of whatever you're working with for these kinds of things. Okay. And now we are going to, oops, I'm just going to get rid of this print. I don't know why I had it down there. So now to add the chart, one way to just do the chart is you can just say print class chart. It'll show up in your console. So let's go ahead and do this. And I think I got everything right here. And there you should have a chart that pops up like that in relatively no time. Right? So, cool. So this is how many pixels are in how many water pixels we saw in the image. So you can see the reservoir was built in around June, the beginning of June, or it was when the dam put in, they started filling up. So you can see it fill up, and then it does some stuff over here. There's a little bit of noise in our data up there, but you can see it's filling up, and then it fills really up, and then you have this really sharp drop. So that's really interesting, isn't it? So we'd like to investigate, what happened at that time period. What exactly went on there? And wouldn't it be nice if you could just click on the chart and it would show you what the water classification was at that time, right? Well, we can do that. We can actually put in the functionality to make that happen. And instead of making you type all of this, I would just go to the website. Yeah, go to the website because it's a long command and it's a little bit and it's pretty confusing. I'm not going to explain how it all works right now. Let's see. Yeah, it's this whole part, making chart interactive. So go ahead and grab all of that and copy it and just stick it at the end of your script. Feel free to go through that later and try and figure out what it does. It's really cool. It's really neat how it works, but that's beyond what we're going to cover today. But for now, you just have this snippet of code that you can then adapt to your own charts, and I found this to be an extremely useful tool. So go ahead and paste that in. We should be good, and hit run again, and we'll see. Okay. So we got this label that now says click a point on the chart to show the image for that date. So now you can click, and it will change to the image that was that day, and I'm zoomed out a little bit, but if you zoom in, you see where we defined water in that area is defined as blue. So now you can use this chart to explore and figure out what exactly is going on with this reservoir. So I'm going to give you a few minutes. Take a look. See if you can figure out what's going on. What happened, specifically what happened here in July of 2018. So if anybody's got a guess, you can let me know. Shout it out. Well, I guess so. Let's back up. Did everybody get this interactive thing to work? Did it work out? Very cool. So what happened? What happened here? All right, the dam actually collapsed and it broke, and it actually broke the day before, on July 24th, the day before the observation we have, and so this is kind of a dramatic example of the kind of thing you can look at with this type of data. A little thing about this region, Southeast Asia, in the middle of July, it's covered in clouds. You cannot see this with Landsat data at all. It's very rainy, and in fact, that's what happened. Is it filled up a little bit beyond where it should have. It was actually a temporary dam put in while they're building the real dam, and it failed. Some other things you can see in the image, if you look downstream, you can see parts where, you can see these parts where there's like some extra water downstream here, and if you look farther downstream, there's actually a lot more water down there than there was the day previous. So the bigger point I was trying to make with this is that you can not only make a nice time series out of your data, but you can also add a little interactive element to make it much easier to explore your data, right? Because if you didn't have this, then you'd have to go back to your collection, filter it for the date that you want, pull out the one image, plot it, pull out another image, and plot it. This way you can just kind of look through. And there's all kinds of different very nice like UI shortcuts that you can build for yourself. So you can make really nice little tools for yourself and also for sharing your data. You can give this to somebody and they don't have to know how Google Earth Engine works, and they can still play around and explore your data. Okay, so does anybody have any questions on that? How that worked? All right, very cool. And I think this is where we're going to end. I've got some some closing comments. Again, feel free, go back through those tutorials if you want to and take a look at some other stuff in there. We explore a little bit more about temporal and spatial reducers, talk a little bit more about time series in these other ones, and talk a little bit more about classification in that one at the end. You can go through them at your own time. Let's see, what are my closing thoughts? Okay, I already shared with you the developer forum, the guide, the catalog, all of that stuff. I guess here, just on this page, on this closing thoughts page, there's some useful resources to look at. And you can always, as always, down at the bottom, there's this contact button that should send to my email. So you can let me know if you have any questions. Let me know if you learned something cool and you went back and did some awesome research with this. I'd love to hear that. Yeah, and that's all that I have. So thank you.